Okay, this is the video with the second half of the problems for kind of talking about strategies, how to put it all together, and select a strategy. So as we start this, I want to review the strategy tree again. And again, I would ask you or suggest that you print this off from the PDF that's on the Mr. Felling site with the links to these videos. Um, the main idea here is that we're dividing between discrete and continuous. And in the first video, we haven't seen any continuous ones, so we'll talk about that a little bit later. In this video, we'll have some problems that get into that. But basically, discrete probability problems are ones where we're talking about specific values, like counts. So many different things can be done where you're talking about counts. And even if you have a probability like 0.6, right, it could still represent something where it's, the number of tails or something. Well, number of tails is an integer, and so that's a discrete situation. And then occasionally we have things that ask for typical values or something like that. That's expected value, but usually we're talking about probability. And in the the first half of the video here, video A, we mainly focused on single event and multiple event with or and cases. That was it, like that. So I wanted to briefly talk about some of the rest of the tree. If you believe that you might have multiple events here, but you're not sure what's going on, there's some other clues in the wording that might help, right? If the problem says that events are independent, then that means a tree diagram would usually be good, right? Or you could use the simplified version of the AND formula. If the problem says disjoint is a special case for OR, so that means a Venn diagram or the simplified OR formula, right? If it seems like you could represent the events in sequence, like one event and then another. For example, let's say that a patient is a male or a female, and then that patient could be colorblind or not colorblind, right? So, I mean, first your gender is determined, you're male or female, you're born, and then we can determine later with a test whether you're colorblind or not, right? So you could think of those events as in sequence, and that's where we use the and/or rules together, or a tree diagram. The tree diagram is a really good strategy, right? If you have a large list of options, like those problems where you're talking about Wi-Fi and GPS and leather seats as options for a car, and there's a whole bunch of numbers together, a Venn diagram is usually the best strategy for that, right? And if you have conditional probability with multiple events, you could represent that as a tree, but then you might have to use the Bayes formula structure to go backwards through the tree for conditional probability, and forwards is just a portion of the tree, okay? All right, and then if you have multiple trials with constant probability, we'll start getting into problems like that here. Then you can potentially use one of the three standardized models, the binomial model, the geometric model, or the Poisson model. And the difference is the binomial model is when you're talking about k out of n successes, so like 2 tails out of 10 trials or something like that, right? And if you have large enough n, sometimes it's better to use the normal approximation. We'll see a problem like that, right? If you're interested in when is the first success, then that means you use the geometric model. And if you don't have a probability, maybe you just have a typical value or an average value, right? You don't have the number of trials, or you don't have the p, or both, then that's where Poisson comes in, okay? And then there's a whole series of things related to continuous variables, right? Average value uses expected value or an average value formula. That depends on the nature of the f of x that's given. If you have probability problems, sometimes you're given a probability density function, then use calculus for that. If the PDF is not given, which is more likely, then it could either be a standard kind of shape, like uniform or exponential, and there's formulas for the PDF in that case, or it can be a normal curve. And then if it's a normal curve, there's kind of 4 things that we encounter in high school probability. We either need an area where we use normal CDF, or we need a boundary where we use inverse norm, or we have multiple distributions where we're transforming one normal curve to another using the transformation rules before we use these other 2 formulas. Or we have some sort of changing units, right? I'm sorry, this is the transforming one. If you have multiple distributions, then you have to combine, and the main idea there is that the means follow algebraically, but the standard deviations add, the variances add according to the Pythagorean theorem of statistics. So that's kind of the whole tree, and we're going to look at some more advanced problems in this video. Okay, so the first one says a shopping mall has 3 automated teller machines, ATMs. Because the machines receive heavy use, they sometimes stop working and need to be repaired. Let the random variable x represent the number of ATMs that are working when the mall opens on a randomly selected day, and the table shows the probability distributions. A, what is the probability that at least one ATM is working when the mall opens? And B, what is the probability that all three ATMs are working given that at least one is working? So pause this and then give it a try. Okay, so the way I would look at this, first of all, is for A, right, the probability that at least one ATM is working, right? There's a couple ways we could think of it. You could think of it this way, that at least means that the one case will work, the two case will work, the three case will work. There's three different cases, so this becomes a multiple event, right? In fact, if we were to look at, let's look at the tree here. This is definitely a discrete probability problem. It's probability, right? And we're talking about an OR situation because for the at least one case, that's when one or two or three ATMs work, right? So that means the OR case right here. And what are our strategies for that? We could use a Venn diagram, or we could use the OR formula. And if there's no overlap, then we get to use the simplified OR formula. So I think on this one, I'm going to choose to use the OR formula. So here's the OR formula written out. And the simplified version is if we have disjoint events, then that means that the probability of A and B happening would be 0. And that's true here, right? If we have one ATM open, then it can't be true that we also have two. So 1, 2, and 3, those are all disjoint events. And so that means we can write something like this. The probability that at least one ATM is open is just equal to the probability of 1 being open plus the probability of 2 being open plus the probability of 3 being open. And we don't have to subtract anything because there's no overlap. Right? So you might have thought just from looking at the table that all I really need to do is just add up the probabilities and you'd be correct. Right? We're just going to add up because this is an OR case. Right? So that turns out to be 0.85. Right? Now there is a second way we could also do that problem if we wanted to. We could have used the complement. A lot of times when we see the words at least, the complement is another way to do it. The probability of at least one ATM being open, that's equal to 100% of the cases minus all the cases that are the opposite. So what's the opposite of at least one being open? Well, that would be this one case here that none are open, that none are open. So if I just did 1 minus the 0.15 probability, that also turns out to be 0.85. So we could do that either with the complement or by just using the OR addition and adding up the cases that are at least. Okay? Okay, for the second one, the probability that all three ATMs are working given at least one is working, the fact that it's got this given case in here, that makes this a conditional probability. And so just to remind ourselves about conditional probability, you have to write it like this, where you have probability of something given a condition, and then the condition is what determines the denominator of the fraction, and the numerator is the portion of that condition that meets the event. Right, so it's a conditional sample space. So if I wanted to think of this problem as a conditional sample space, we would write this. The probability that all three are working given that at least one is working. So I could think of that as a fraction, and the at least one part has to represent the conditional sample space. So the at least one part would be this. This is the conditional sample space here, right? 1, 2, and 3. So if I just added those up, because it's 1 or 2 or 3, we have that 0.85 that we found in the first part, right? And then the numerator is going to be the part that's 3 only. So just the portion that's 3. It's this portion of the conditional sample space, the 0.24. Right, so 0.24. So the correct way to structure this would be 0.24 divided by 0.85. And the answer to that turns out to be 0.2824. So that's the correct answer for this. Okay. Could we do this another way? There is another way we could do this. The conditional probability means we could use the conditional probability formula. So let me see how we could do that. The way I remember it, rather than memorizing the formula, is I memorize a picture, right? If I have conditional probability, if 3 is, we're looking for the probability of 3 given that at least one happened, then that means the at least one happened had to be first. So I could write it like this. If I thought of these as being in sequence, at least one ATM works, and then 3. So if I wrote probabilities for that, this would be the probability of at least one working, right? And this one would be the probability of 3 given that at least one works. And then out here would be the probability of at least one and 3, right? multiplying together. So the and formula says we multiply, right? The probability of at least 1 and 3 is the probability of at least 1 times the probability of 3 given, probability of 3 given that at least 1 works. Okay, so if I solved that for the conditional probability I'm trying to find here, right, that would be the probability of 3 given at least 1 works, which is what I'm trying to find. That's going to be, if I divide both sides by this at least 1, the probability of at least 1 and 3 divided by the probability of at least 1, right? And so we know that the probability of at least 1 is the 0.85, right? But what is this probability of at least 1 and 3? So if I just thought of the tree together, or the table together, it would have to be that at least 1 is true, which is this, and also 3, which is this. So it'd be the overlap of that. And it's just the 3-case probability, 0.24. So that's another way to get the 0.24 over 0.85. Okay, and in these videos, we're taking an extra amount of time because we're trying to look at all the strategies that, if possible, or at least some multiple strategies, that will work. And both of those are equally good. It's just a matter of what you remember and what you feel most comfortable with. Okay, let's move on to the next problem. It says, assume, oh wait, there we go. Assume that 24% of adults smoke cigarettes and 16% of smokers develop lung cancer. About 2.2% of non-smokers develop lung cancer. A, is developing lung cancer independent of smoking? Explain. B, what is the probability of developing lung cancer in all adults, smokers and non-smokers together? C, if a person develops lung cancer, what's the probability that they're a smoker? Okay, so pause this and then give it a try. All right, so I think let's look at the tree, the strategy tree, and see if we can figure out what's going on. The first thing it says is developing cancer independent of smoking. So I want to take a quick look at the tree here. If we're talking about independence, I see that here in this, right? It has to do with the simplified AND formula, and therefore it's a special form of AND, right? So I would probably just remember that for independent events, that means that the probability of one thing happening can't change if the other thing happens. It has to be the constant, right? If two events are independent, if, say, the probability of event B is the same as the probability of event B given A, which is the same as the probability of event B given A doesn't happen. And I can check any two of those, right? And there is another way to do it with the formula here, but I actually really prefer this way. This way is the way that gets to the heart of what independence is. So if I wanted to check that, what I could do is pick, I could say something like this. What's the probability of cancer given that somebody is a smoker? And what's the probability of cancer given that they are not a smoker? So I'll write it this way, not a smoker, okay? And if those two probabilities are equal, then the probability of cancer doesn't depend on if you're a smoker. It just is a certain probability. So it says here that about 16% of smokers develop lung cancer. So that's the conditional probability. If you have lung cancer, if you have smokers, the probability of developing lung cancer is 16%. That'd be 0.16. But it says if you're a non-smoker, the probability of developing lung cancer is 0.2%. And since those things are not equal, it means that having cancer and smoking are not independent. These are not independent, right? Because the probability of cancer is depending on whether or not you smoke. Okay, let's look at the next part. The next part says if a person develops cancer, what's the probability that they are a smoker? Okay, so that's definitely a discrete probability problem because even though the probabilities are percentages here, right, the underlying variable is the number of people who smoke. Numbers of people who smoke are integers, and so that's definitely a discrete problem. It's a probability problem. Maybe at first we're not sure here, but this is an example of events in sequence, right? You can kind of consider that people first decide whether or not they're going to smoke, And then if cancer is caused by that or potentially caused by that, then they may get cancer, or then they go in for a test to determine if they have cancer. So you can think of that as events in sequence. And if it's a conditional probability, then we might have to go forward or backward through the tree. So a tree is really the best way to investigate it, I think, using the and or rules. If we have to go backwards, we'll use this Bayes formula kind of construction where it's probability of paths. And then if it's a conditional probability, we'll again evaluate the denominator from the condition and the numerator from the event space within the condition. So let's investigate this with a tree. Okay, for B. I think we should investigate with a tree. So first, we have a person may smoke, or they may not smoke, the opposite of smoke, complement of smoking. And it says 24% of adults smoke cigarettes, so this probability would be 0.24. And if I took that and subtracted from 100%, the other 76% would therefore be non-smokers. All right, then if they did smoke, then they may get cancer, or they may not get cancer. Right? Same thing if they didn't smoke, they may get lung cancer, or they may not get lung cancer. Okay. So it says that 16% of smokers develop lung cancer. So if you smoke, there's a 16% chance of developing lung cancer. If you don't smoke, there's a 0.02 or 0.2%, so 0.002 probability of getting cancer. And we could also figure out the other probabilities, because if 16% of the smokers get cancer, then that means 84% of the smokers do not get cancer. And if 0.2% of non-smokers get cancer, then 99.8% of non-smokers don't get lung cancer. Okay, so there's the complete tree filled in. Now we can use this to solve. So for part B, let's see, we're trying to find the probability of developing lung cancer in all adults. So part B is asking us for the probability of developing cancer, period. Okay, so if I look at the tree, where is cancer? Cancer is here. I'm going to change colors here. Cancer is here, and cancer is here. So the probability of getting to this first check mark is you'd have to be a smoker, 24%. You'd have to have cancer given that you're a smoker, 16%. And since the smoker and the cancer have to happen, you'd multiply those two. Right? And then on the second check mark here, you could be a non-smoker, 76% chance, get cancer given that you're a non-smoker, 0.002, and because both of the first thing and the second thing has to happen, you'd multiply. And then because you can have this way, this check mark or this check mark, we're going to add those probabilities. So the way to compute this would be 0.24 times 0.16 plus 0.76 times 0.002. And when you do that in a calculator, that turns out to be 0.0399. Okay? All right, so that's the way that I would do the first problem, the first part. Okay, for part C, it says, if a person develops lung cancer, what's the probability that they're a smoker? So we're going to use the same tree, but this time, this is a conditional probability, right? For part C here, we're talking about what's the probability that we develop cancer given that we are a smoker. Wait a second. No, that's wrong. I got it backwards. It says, if the person develops lung cancer, that makes this the condition. What is the probability they're a smoker? So actually, yeah, you have to be really careful about carefully looking at the order of the words. This is really the probability that we're a smoker, and the if a person develops lung cancer, that's actually the condition. Okay, so this is going to be a conditional probability. Right, so the bottom is going to be everything, all the ways you can get cancer. In fact, I'm going to write it this way. It's all the paths that end up at cancer, right? And on the top, that's going to be just the paths to cancer that went through being a smoker. Okay, so I can use either counts or probabilities when I do a formula like this, so I'm going to stick to probabilities. So we know that all the paths to cancer are this path to cancer, right? Or this path to cancer. So, and that's the probability we just found before. So 0.24 times 0.16 plus 0.76 times 0.002. Those are all the ways we can have cancer. And then out of those ways, the ones that met the event smoking was only this path. So that would be the 0.24 times 0.16. So it's a fraction of the paths. All right, and if you plug that in a calculator, that turns out to be equal to 0.9619. So if you have lung cancer, there is a 96% chance that you are a smoker. Now that's not the only way we can do this. We can also use the conditional probability formula if you feel more like using the formulas. So let me just write it out. You can derive it from a tree like we did in the previous one there. So if I have probability of smoker given cancer, you could, instead of using a tree, you could say, okay, this is going to be the probability of being a smoker and having cancer, right, divided by the probability of having cancer. And that actually is just another way to write out what we did in the tree, right? The bottom probability here, this one right here, is all the ways of having cancer. And the top is the intersection of that with being a smoker, right? So you could also think of that as using the conditional probability formula. I personally like the tree method because then I don't have to memorize things with symbols more than necessary. Okay, let's look at another problem. This one says, if the odds for winning a horse race are 7-3, and the person betting will win $10 if their horse wins, then how much should the person have to bet in order for the game to be fair, where fair means that if they were to bet on this race many times, they would break even in the long run? Okay, give this a pause and try it out. Okay, so let's look at the tree again. Well, we're talking about winning or losing, and actually this is having to do with how much we win. So it looks like there's really only two options. You can either win $10 on your race, or you can win $0 because your horse didn't win. So that's an example of a discrete probability problem, all right? But it's actually not probability. We have to figure out how much we would win in the long run, right? So that can be thought of as the mean of the distribution of possible winnings, right? Or it can be thought of as the expected value for the winnings. So this is going to be an expected value problem, and it's not one of my special cases here because I don't have constant probabilities. So we're going to use the discrete event or the discrete expected value formula. That's going to be the strategy. And by the way, these little numbers here, like 8, that means that was covered in lesson 8 videos if you want to go back and review that specific idea, right? So for general models, the expected value formula is this. We take the sum of the individual data values times their probabilities, okay? And you could actually do it in the calculator as well, but we'll do it both ways. So for me to do that, it means I'm going to have probabilities to start with, right? So the probability that we win, so the way odds works is if we say 7-3, that means there are 7 wins for every 3 losses, right? But probability is the number of wins out of the number of total races, right? So first we need to convert this odds to a probability. So that means there's 7 wins for every 7 plus 3, or 7 wins out of 10. There's a 70% chance of winning. We need that probability in order to do the problem. And then if I wanted to do the expected value will be the sum of data values times their probabilities. So let's see, if I were to make kind of a table, let's actually make a table of this. Let's have a random variable x be the dollars that we win, and then the probabilities associated with that. So we could win no dollars, right? Or we could win $10. And we win $10 70% of the time. That means we win no dollars 30% of the time because that's the only other possibility. So my sum here would really be that I can win, let's see, I can win $0 30% of the time, so that data value times the probability, plus I could win $10 70% of the time, right? So that turns out to be $7. And that means we'll never actually win $7, but we'll win $0 sometimes and 10 sometimes, and in the long run, it's going to average out to $7 per play on average. So that means we should be willing to bet up to $7, but not more. If we had to bet $6, we're going to win money in the long run. If we had to bet $8, then we wouldn't win, right? Also, there's a second way that we can find that expected value. It's the mean of that probability distribution. And so let me go ahead and get a calculator on the screen here, and we'll take a look at that. So the other way If you have all the possibilities written out in a table, is you can enter that in a calculator's lists. So for example, I could go ahead and enter the two data values, 0 and 10, as possible data values in list 1, 0 and 10. And then in list 2, I could set to put their corresponding probabilities, 0.3 and 0.7. And then I could say quit out of that, go back to stats, and then do one variable statistics to calculate the statistics on this data set. The lists are in list 1. The frequencies or probabilities are in list 2. And if I hit calculate, it tells me the mean. So the mean of that distribution is $7. It also tells me the standard deviation is $4.6. But what I'm after here is the expected value, which is that very first line, x bar. The mean is 7. Of course, we really should use this symbol because it's a population, but the calculator considers everything entered into it as a sample, so it uses the X bar symbol. All right, so that would be the answer, $7. Next problem. If the average hurricane frequency is 8 hurricanes per year, what's the probability that in a randomly chosen year we would have less than 2 hurricanes, or more than 10 hurricanes, or exactly 8 hurricanes, the average number of hurricanes? So pause this, give it a try. All right, let's look at our table of strategies again, or tree. Well, we're talking about numbers of hurricanes, so you can't have 1.8 hurricanes. So this is, integers, and that makes this a discrete probability problem. It is a probability problem. And in this case, we don't have a probability, but we have an average amount of hurricanes, right? That implies that the probability is roughly the same year to year to year. Some years we have more, some years we have less, but we can express it as an overall average or an overall probability. So that's like saying we have multiple trials with constant probability, where the trials are the years, right? So first of all, we could ask this question: do we have k out of n successes where we have n is known? And the answer to that is no. It's not like I'm saying that we have 5 years out of 20 years where we had a certain number of hurricanes, right? We're not given like a total number of years. There's no n in this problem. Is this about, so I just crossed this one off the list. If I'm looking at this one, when is the first success? Am I concerned with what's the first year when I have at least 3 hurricanes or something like that? This isn't a problem about that, like when is the first success where I define success as a certain number of hurricanes, right? This is the last case here. I'm talking about k out of n successes, or I don't know the probability. That's the key. I actually don't have a probability. I have an average number of hurricanes, but I don't have a probability. So this is where we're going to use the Poisson model. Now, all 3 models work the same way. They're just used in different situations. This one's going to require the Poisson model. So here's a comparison of the models. It's just like all the others. We have to have only 2 outcomes. These are the things we have to have. And in this case, it would be that you either have a hurricane or you don't have a hurricane. So a yes would constitute a hurricane, right? The probabilities of the trial don't have to be independent. In other words, we could go through spells where a few years in a row we're more likely to have hurricanes, and the probabilities are affecting each other. So that doesn't prevent us from being the Poisson model here. But the main thing is here you need a typical or expected value, which we call lambda. Right, so here the lambda would be 8 hurricanes, right? Because we average 8 hurricanes, right? And in that case, we're going to write a model like this. And if we're going to find an exact probability, we'll use the p version. If we're taking a left side, it's the CDF, the cumulative value, and the right side is 1 minus the c. So let's go ahead and take a look now. For part A, if I let my random variable be the number of hurricanes, and then I've got probabilities here, I could have no hurricanes in a year. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's really no limit to this. It's not like I have a limit to the number of hurricanes I could have, right? So there's no n value there, right? But I want the probability that a chosen year would have less than 2 hurricanes. So less than 2 hurricanes would be only 0 or 1, right? Now I could do that 2 ways. I could find that probability by doing Poisson PDF, right? And for the Poisson function, you have to give it the lambda value and then the particular x value that you're interested in. So if the average was 8 hurricanes, if I wanted to find the probability of having 0, I could put a 0 there. And then it could be a 0 or a 1, so then I could add the Poisson PDF Poisson PDF, if the average number of hurricanes is 8 of having 1. So that would be one way to do the problem. Or if I want to do it all together, I have a single function for that, Poisson CDF. C stands for the cumulative total from the left up to a value. 8 is the average up to and including 1. And so that's the way I would do it. Let's show you how that works on a calculator. Right, if you go to where it says distributions here, I'll quit out of that. Second, and then the variables key. And if you scroll way down or scroll up and wrap around, there's Poisson PDF and Poisson CDF. I'm going to do the CDF version, less typing. The average number of hurricanes is 8, but I want to know up to 1, right? And that turns out to be 0.0030. So this probability would be 0.0030. Okay? All right. The next one says, what's the probability that we have more than 10 hurricanes? So again, I could write out my list here of my random variable representing the number of hurricanes in this case. Goes forever. So I want the probability that we have more than 10, right? So more than 10 would be over here. And so I'm definitely going to use the idea that more than 10 and up to 10 add up to 1. So the probability of having greater than 10 hurricanes is 1 minus the probability of having 0 to 10 hurricanes, less than or equal to 10. And that's going to be 1 minus, and I'll use the Poisson CDF function again. 8 hurricanes on average that we have up to and including 10. And if you plug that in a calculator, that turns out to be 1 minus 0.8159 or 0.1841. Okay? So a left-hand probability, we use CDF. A right-hand probability, we use 1 minus CDF. The last case on here says, what's the probability that a chosen year will have exactly 8 hurricanes? In other words, we'll have an exactly average year. So if I were to draw out my possible list of the random value variables, 11, and so on, right, we're finding the probability of having exactly that one number 8. And that's where we definitely use the P version of the formula. So it would be Poisson PDF if the average is 8 of having exactly 8. And that's just right above the right above that in the list here. We use the PDF version of the formula. If the average season has 8, the probability of having 8 turns out to be 0.1396. Okay. All right, so we'll use the Poisson formulas for that. Okay, let's look at another problem. If a person gives a friend their key ring and tells them to go on ahead and open the front door, there are 8 keys on the key ring, and the person does not tell their friend which key opens the door. So the friend must try keys randomly until they find the one that opens the door. What's the probability that the friend must try more than 4 keys before the door will open? And let's make the assumption that the keys look identical. So she would have to try every key, or he would have to try every key. Okay, give this pause and give the problem a try. Okay, so this one, if I look at the tree again, we have a discrete, right, number of keys. It's a probability problem. We have multiple trials with a constant probability, because if you have 8 keys and they're all indistinguishable, then the probability that any one of those keys is going to work is 1/8, right? And it's this case. We're looking for when is the first success. We're not going to try all 8 keys, so it's not out of 8 keys. We're just going to keep going till we find the first key that opens the door. And that means that we should use the geometric standardized model, right? The geometric model. So the geometric model works the same way as the Poisson model did and the binomial. You have to have 2 possible outcomes. And yes here would be that the key works in the door. The probabilities must be the same. It would be 1/8 for every trial. They have to be independent, right? One key doesn't have memory about the next key next to it. It doesn't affect each other, so that would be true. And you may or may not have a fixed number of trials, but you're not going to use the number of trials. So I know there's 8 keys, but I'm not going to use all 8 keys. I'm just going to keep going till I get the first one. So then we just get to use the geometric version of those same formulas that we had on the last problem. So if I were to make a variable that is which key opens the door? Okay, well, right, we don't start at 0. We have to try 1 key, so this starts at 1, right? The first key could open it, the second key, the third key, the fourth, the fifth, the sixth, the seventh, or the 8th. Okay, and we're wondering what's the probability that we have to try more than 4 keys. So more than 4 keys would be the right side, right? This probability here is what we're finding. But that and this add up to 1. So if this one over here is geometric, so geomet CDF, right? What do we have to do for geometric probabilities? We have to enter the probability of success on any individual trial and then the particular number that we're interested in. So this would be 1/8 chance of opening the door, and then up to and including 4, right? So the right-hand side, right, the probability that it takes more than 4 keys is going to be 1 minus the probability that it takes less than or equal to 4 keys to open the door. So that's going to be 1 minus the geometric, the left side, 1 geomet CDF, 1/8 probability of opening the door on any one trial, 4. And those probability functions are found in the same location. So if you go second vars and then scroll around, it's the very bottom ones. In fact, geometric CDF is the very bottom one on the TA84. Probability is 1 divided by 8, and we want to go up to and including 4. So this 0.4138 is this number, so it would be 1 minus 0.4138, and that turns out to be 0.5862. So the probability that the person that you send on ahead is going to have to try more than 4 keys before your door opens, 58.6% of the time. Okay, let's keep going here. So in 15, it says, let's see, events A and B occur with the probabilities given. Probability B is 0.6, probability of A and B, or A or B, that's the union, A or B is 0.9, A and B is 0.2. What is the probability of A? Are the events mutually exclusive, and are they independent? So pause the video and give this one a try. Okay. Well, we've got the OR formula and the AND formula. Let's look here. Even though we're only given probability numbers, which are always fractions or decimal, presumably this is some sort of underlying probability that's discrete. How can I tell that, right? I mean, if it was continuous, we would have to either know that it's a normal curve of some kind, right? Or we would have to have a PDF that's given in some way or some other way to find a PDF. This just doesn't appear to me to be a PDF kind of problem, so I'm going to make the assumption that the underlying structure is discrete. Okay, so it's a probability problem. We definitely have multiple events because we have event A and B, and so we're talking about the OR and AND formulas, right? All right, so things to know about that. Well, a compound event, right, OR formula case, we could use the OR formula, and the reason that I like the OR formula is the OR formula includes both OR and AND in it, right? It's got the OR and it's got the AND case in it in one formula. The AND formula, by contrast, say the probability of A and B, right, is the probability of one of the events times the probability of the other event given that the first one occurs. That's got a conditional probability, but it doesn't include the OR case, right? There's no OR in that formula. So I think the right formula for us to use here to try to solve for part A is the general OR formula. So what we could do is write it out, right? We could say probability of A or B is equal to probability of A plus probability of B minus the probability of A and B. And then we can just fill in what we're given. So this 0.6 here is probability of B. This 0.9 is the OR probability, which is on the left side. And the A and B is here, 0.2. So that just leaves one thing left to find. And that means we could just algebraically solve for probability of A, right? 0.9 equals probability of A plus 0.4. And when I subtract that, that means that the probability of A has to be 0.5. Okay, so far so good. Let me go ahead and write it up there too. Probability of A is 0.5. I don't have a separate thing for this, right? Yeah, okay. So let's call that 0.5. Okay. And then let's take a look at the second part. So the second part is, are the events mutually exclusive, right? So mutually exclusive has to do with whether or not they're disjoint, right? A mutually exclusive, or another way to say that is disjoint effect, is when you have a Venn diagram like this. There's no overlap. And that means that the probability of A and B would have to be 0. Right? But in part B here, in part A, we found that we're given that the probability of A and B is 0.2, 0.2, that's not equal to 0. And that means that there has to be an overlap. In other words, if I were to draw the Venn diagram, I would have to have A and B overlap so that I could put 0.2 there in the middle. So the fact that that's not 0 means the answer to this is no. It's not mutually exclusive, and the reason why is because probability of A and B is not 0. That would be the way we could answer that question. Okay, let's look at the part C. Part C says, are events independent? So if I kind of look through my independence thing, the thing that makes things independent, we already mentioned, is if you can check any two of these probabilities, like probability of B given A, probability of B given not A, and if any two don't match, then that means one probability is changing depending on the other, and it's not independent. Right, so what I could do is maybe I could find, we know probability of B, but let's compare that to the probability of B given A. I think we could compute that one. Okay, the way I remember conditional, I don't memorize the conditional probability formula. I just think, okay, if it was written like this, B given A would have happened first because it's the condition. So I put in event A, and then I think of event B happening as second, even though they may or may not be happening literally in sequence. You can think of B depending on A. And so if I had like a whole tree here, right, this would be the probability of A, this would be the probability of B given A, and this would be the probability of A and B. So this is how I recreate the formula from memory, right? Probability of A and B is the probability of A times the probability of B given A, right? So what I can do then is just solve that for this by dividing both sides by that. So the probability of B given A is the probability of A and B divided by the probability of A. Right? Now the probability of A and B is given as 0.2, and the probability of A, we found out in the last part, is 0.5. And so that means the probability of B given A is 0.4. So now I can ask the question, is it true that the probability of B is equal to the probability of B given A? Well, the probability of B was given as 0.6, but the probability of B given A we calculated as 0.4. That means the probability of B is changing depending on whether A happens. Since these are not equal, it means A and B are not independent of each other. They're not independent. Okay, so that's how we would check for independence. Okay, let's do another problem here. So this one says, a game of skill at a county fair consists of throwing ping pong balls into buckets. A game consists of throwing 4 balls at the buckets, and to win, the player must have all 4 balls land in a bucket. On any individual throw, the ball lands in the bucket 30% of the time. A, if the player plays this game 1 time, what's the probability they will win that game? B, if the player plays the game 5 times, what's the probability they will win at least one of the games? And C, if an older sister is determined to win that prize, which is a stuffed animal for her little brother, how many games on average should she expect to have to play in order to win the prize for her brother? Okay, pause this and then give it a try and unpause. All right, so, you know, the thing I'm focusing on here is it says that the ball lands in the bucket 30% of the time. That means that there's a constant probability every time I do a throw. I definitely have a discrete situation here because I'm counting either the number of balls landing in buckets or the number of games that I win. It's a probability problem. Multiple events because I have to have multiple trials of throwing balls into buckets in order to have a game be win. And I specifically have multiple trials that have a constant probability of 30% of winning. Right? So that means we can use one of our models, the binomial, geometric, or Poisson models, to analyze this. Right? But we're generally talking, I think, about this first case. We're talking about some number of successes out of a number of things. Like, for example, we're talking about 4 tosses out of 4 in order to win a game. Or we're talking about a certain number of games out of 5 that we have to win. So for both of those, A and B, I think we're going to use the binomial situation. Do we have a large N? No. All the numbers here are pretty small. 4 tosses for a game, 5 games. So we're going to be sticking with the binomial model. Okay, so we have to have 2 outcomes. And that's going to change depending on the problem. We'll analyze that a little bit further. The probability is different for each trial. We'll investigate that individually. The trials are independent. Presumably, every time you toss the ball, it's independent of any other trials. And we have a fixed number of trials here. So we're going to use the binomial model. Okay, for the first one, where we're talking about the probability of winning the game, then in that case, let's look at what each of those things are. What is yes and no in this case? Yes would indicate that we have a ball gets in the bucket, okay? Is the probability of that constant and independent? Yes, the probability of that is 30% of the time. That happens with a 30% probability. What about the number of trials? Well, in this case, we're talking about a game, and a game consists of 4 tosses. So that means we have a fixed number of 4 tosses. So that means we definitely have the binomial situation here. And we can use the binomial one. So if I make my random variable x, it's going to be the number of balls that go in to a bucket, right? And that could be none of the balls go in, 1, 2, 3, or all 4 balls in that game go in. So we're trying to find the probability that we win the game, right? So winning the game means that all 4 balls have to go in. So we have to have exactly 4 balls go in. That's a specific case. So we're going to use the binomial PDF function. And for binomial, we have to tell it the total number of trials, right? That's usually called x. And then we have to have the probability of it going in the bucket, which is 30%. And then we have to have the particular k value. We want to know 4 of the 4 trials. And so that is also in those same places we've been looking. If you go to second vars, it's not as far down. Binomial PDF, because it's a single case. The number of trials is 4. The probability of winning is 30%, that bucket going, or ball going in the bucket, and 4. And so that turns out to be 0.0081. 0.0081. So that's the probability of winning a single game. We're going to win a game 0.81% of the time. Okay, let's look at the second part. For the second part, we're playing the game 5 times. We want the probability that we will win at least one of the games. The same reasoning is true. We're talking about the same probability, but this time the n is going to be the number of games, and we're talking about winning at least one of the games. So that's some number of wins out of the 5 games with a constant probability, right? If we look again, we have to have the same things. Let's actually just jump in there and start analyzing it. So for part B, right, what would yes and no consist of? Yes here consists of winning a game, right, rather than a toss going in. And is the probability independent and constant? Yes, the probability is what we computed in the first part. There's a 0.81% chance of winning an individual game, okay? And then let's see, do we have the trials? Do we have a fixed number of trials? Yes. We're talking about playing this game exactly 5 times. So in this case, we have a 5, and that makes this, again, a binomial situation. So we're going to use the binomial model. So the random variable this time is going to represent the number of games that we win. And we could win none of the games, 1 of the games, 2 of the games, 3 of the games, 4 of the games, or all 5 of the games. Right? Now, if we want to win at least 1 of the games, so that's going to be this, right, on the side, 1, 2, 3, 4, 5. I could do binomial PDF for 1, 2, 3, 4, and 5 and add them, or I can just say that the probabilities add up to 1 here. If I add these, they add up to 1. So I could say it this way: the probability of winning at least 1 game is equal to 1 minus the probability of the opposite, winning none, no games. Right? And the probability of winning no games would be binomial. I could either use PDF or CDF. The CDF would be the cumulative total, but it would only be a cumulative total of 1. So I'm going to stick with PDF. Out of 5 games this time, the probability of winning a game is the 0.0081 we had from the first part, and 0, that we would win no games at all. So this is going to end up being 1 minus 0.96015, and so that turns out to be 0.0398. So if I play the game 5 times, the probability that I will win at least one of those games is only about 4% of the time. All right, complicated problem, but a lot going on here. The last part says, an older sister is determined to win the prize for her brother. How many games on average should she expect to have to play in order to win the prize? So the thing I'm focusing on here is this word expect. That means we're talking about an expected value. Okay, and an expected value right? We could use the the expected value formula if I had a general thing, right? But the expected value is also the mean of the distribution. And if I have a standardized one, like the binomial or the geometric model, then I can use the mean for that particular kind of distribution, right? So we know that this situation is a binomial, right? So the binomial model, right, its distribution shape depends on the probability of success. It's perfectly symmetrical and normal-like if the probability of success is 0.5, right? But here, the probability of success is, the probability of winning an individual game is 0.0081. So it'll be skewed in some way. And there are formulas for finding the mean and standard deviation of that distribution. What we're interested in is the expected value, which is the same as the mean. So it's really going to be n times p. Wait a second. Am I right? I jumped right into the binomial, but let's just double check that assumption, right? That would mean that we're going to play a certain number of games and we're going to win a certain number out of that. Is that really true in this case? Like, this doesn't say that the older sister is going to play 20 games, and what's the probability that she will win at least one of the 20 games that she'd win? That doesn't say that at all, right? Actually, it doesn't give us a total number of games. It just says she's determined to win the prize. Well, if she's determined, then presumably she's not going to let, I'm only going to play 20 games and that's it. She's going to keep going until she wins this for her brother. Okay, well, if that's true, then I actually don't have an endpoint. I'm just going to keep going until I have the first success. Okay, so until I have the first success actually means we're talking about the geometric function. That has a different shape. It always looks like a decaying exponential function. And its mean, so its expected value, turns out to be 1 over p. So what I'm really going to compute is what 1 over p is, right? Yeah, let's go ahead and solve for that then. If all I'm looking for part C is the expected value of what we now know as a geometric distribution, it's just going to be the mean of that, which is 1 over p. And 1 over p, in this case, p is the probability of winning a game. Every time I play, I have a 0.0081 probability of winning, right? So if you take that and plug it in a calculator, it turns out to be 123.45. So she should expect to have to play, on average, 124 games before she wins that prize for her little brother. Now, is that worth it? Probably not. I'm guessing she has to play a dollar. Usually carnival games cost $1, right? So if she has to pay that, she's going to be paying on average $124 to win this stuffed animal for her brother. And I'm suspecting that the animal would cost a whole lot less for her to buy if she bought Frets, right? So for when you're going to go to the carnival or the state fair, right, definitely play those games if it's fun, right? But it's not good to play those games if your intent is to win the prize. You're always going to lose money in the long run. Okay, let's take a look at another problem. This one says, in a group of 3 people, what's the probability that at least 2 were born in the same month? So pause this one and give this one a try. Okay, so what do we have here? We're talking about numbers of people, definitely a discrete problem. It's a probability problem. I think there's multiple ways we could view this. One way would be to consider this to be a single event. In other words, we're just going to consider all the ways that we can have the 3 people interact, right? And then just consider them all at once as a single event. And we'll just say, okay, how many of those interactions would result in at least 2 of them having the same month? Let's try analyzing it that way first. Okay, well, if that's true, then every grouping of 3 people in terms of their birthdays would be equally likely. Presumably, everybody has the same probability of having the same or a particular month for birthday. And that means we have to use various kinds of counting strategies, right? So we're going to be talking about whether or not people are born in the same month. And we're going to be using this one right here, the multiplication principle. When I have multiple choices to make and every possible choice in one box can be paired with every other choice. So for example, if I have to choose a month for the first person in the group of 3, then I have a certain number of choices for the second month, and the number of choices for the first month can be paired with every possible combination of the choices in the second month. All right, so let's analyze it that way. Let's say we're talking, first of all, I've got the probability that at least 2 share the same month birthday, have the same month. from experience, I have found that whenever you have problems with at least, we should at least consider using the opposite of that, right? Because often those are easier. The complements are often easier to find. What's the opposite of having at least two people share the same month? The opposite of that would be to have none that share the same month. Right? In other words, all three of the people would have to have different birth months. That's actually easier to count. Okay, so we're going to do this case, probability equally likely, the probability of that none share, right? So that's going to be a count in an event space and a count in the sample space. So let's look at each of these individually. The sample space is going to be all the number of ways that we can have birth months without any restriction, no restriction at all. So if I were to think about the first person, let's make a box for the first person, the second person, and the third person. Okay, and then the first person, right, they could have one of the 12 months. There are 12 possible months. So there's 12 ways that the first person's birth month could appear. Right, the second person, also all 12 months are available. And then the third person, also 12 months. And the multiplication principle says I can multiply those together. And that gives me that there are 1,728 different ways that three people can have their birth months arranged. Okay, now on the top, I have to define the event. So the event is going to be specifically that we have the number of ways that we can have birth months if the thing we're trying to find is true, that none of them share the same month. So that maybe I could say it with birth months not the same. So I'm going to use that same strategy, multiplication principle with boxes, a box for the number of months for the first person, the second person, and the third person. So the first person could be born in any of the 12 months. But the second person, right, let's say that the first person was born in March. The second person couldn't be born in March. So there's only 11 months late choices for the second person to be born. And once we've used up 2 of the months, 10 of them are left for the third person. And if I multiply those out, that turns out to be 1,320. So this would be 1,320 out of 1,728, and that probability turns out to be 0.2361. 0.2361. So if you have 3 people and you're just considering the month of their birth, right, there is a 24% chance that that none of them share, but we haven't finished the problem yet, right? We still have to do the complement, right? So that's the probability that none share. So the probability that at least one share the same birth month would be 1 minus the 0.2. Sorry, actually I got that wrong. I wrote something down wrong from my notes. This number turns out to be 0.7639. So 1 minus 0.7639, 1 minus 0.7639 turns out to be 0.2361. So the 0.2361 is the answer. It's 1 minus the other one, and the fraction's really 76. So there's about a 76% chance that none of them share the same month, and therefore there's the other 24% chance that at least 2 of them do share the same month. So complement would be the way to do that. It's not necessarily the only way to do it, though. If you wanted to, you could potentially think about this as multiple events by considering each person individually, right? Now, there's a couple ways we could do that. One way to do that would be to say, if I'm going to consider them together, then I have to start thinking about using the and or forms, remembering that we multiply with and we add when we have or. So another way to solve it, and if you try to solve it this way, you could do this correctly, right? We have let's see. So I'm going to still say that we have 728 number of ways for the months to go together. But as far as counting the E case, the number. Let me switch to red since that's what we used. Another way to count the number of ways to have all different birth months is we could just kind of consider, well, could you have like the first 2 people could be the same and then the third one would be different? That would be one way, right? Or you could have, and it could be that the middle person is the different one or the one on the end, right? Or you could have, oh wait, I'm sorry, we're finding the probability. Let me back up for a second. So let's make E the sample size for all three is still 1728 like we saw before. But let's try to directly count instead of the complement. Let's try to directly count the number of ways to have exactly what we're asking for, at least two that were born in the same month. So if that's true, then the first two people could be the same and the third one's different, or the middle person could be the one that's different, or the last two people are the same and the first one's different, or they could all be the same, right? So if I wanted to use boxes again to count that, right, this case here, AAB, we'd have to have choices for the months, right? The first person, we'd have a choice. There's 12 different months to pick from, but the second person would have to match the first person, so there's only one way that can happen. They have to have the same month, whatever that was. And then the third person would have to have a different month, so that would be 11. That turns out to be 132, right? And if I did the same thing for here, I could have the first person could have any of the months. The second person would have to have a different month, so only 11. The third person would have to match the first one. There's only one way that can happen, so that'd be 132, right? Or you could say the first person could have any of the months, the second one could have any of the months, and then the last person would have to match the second person. Again, only one way for that to happen. And they would all be the same, 12 months, right? And then the second person would have to have exactly the same as the first, and the next one would have to have the same as the other two, only one way for that to happen, which is 12. And if you add those up, that turns out to be 408. So you could say that the probability of at least two sharing the same month, that would have to be 408 out of 1728, which turns out to be that same 0.2361. So if you tried to do this without using the complement, this would be one way to do it. If you did it by counting, this would be the correct way to do it. So if you tried it and you didn't get the right answer, this is the right way to do that. And there's another way that you can do this. Let me erase this. I'm still going to try to figure out directly, but maybe I don't even talk about counting at all. What if I wanted to talk about this in terms of the probabilities directly? Right? You could think of it as probabilities. And we're just exploring different ways to solve this, right? We could say, okay, the first, let me use that same reasoning. The first person could have a month, the second one could be the same, and the third is different, right? So if that were true, then the first person would have to, what's the probability that the first person would be born in a month? Well, that would be 100%. They're definitely going to have a birth month, right? Now, what's the probability that the second person is going to have the match to that? Well, 1 out of the 12 months would match the first person, right? So there's a 1 in 12 chance that the second person would match that. And then what's the probability that the third person is different than the other two? So out of the 12 months, there are 11 months left, right? And so that would be the probability 11 out of 144, if I multiply across there. Right? And then also I could have the other arrangements that I listed before, A, B, A. So that would be the probability of the first one being born in a month, 100%. The probability that the second one is born in a month that's different than the first one is 11 out of the remaining 12 months. And then the probability that the third one is born in the same as the first month would be 1 out of 12. So again, we have 11 out of 144. Right? And then it could be BAA, which would mean the first one definitely born in a month. The second one would have to be a different month, so that's 11 out of the 12 months. The third one would have to match the second one, which is only 1 out of the 12 months. So again, 11 out of 144, right? And then the last one would be that they're all the same. So the first one would definitely be born in a month. The probability that the second one would be born in the matching month would be 1 out of 12, and that the third one matched as well would also be 1 out of 12. That turns out to be 1 out of 144, and then you would add those up, right? The probability of having at least two the same, that would be 11 144ths plus 11 144ths plus 11 144ths plus 1 144th, right? And that would turn out to be 34 out of 144, which is also 0.361. So there are 3 different but all valid strategies for solving. I think, frankly, the first one is the least work, right? This one here, where you use the complement and you just count up the number of ways for all the birth months and the number of ways to have different months, is by far the least work. But if you tried one of the other methods, they would work if you did them correctly. Okay, let's try another one here. It says you're dealt 5 cards at random from a 52 card deck. What's the probability that you have a full house, which is a pair and 3 of a kind? So pause this and give this one a try. Okay, this problem can get really complicated because of the counting. There are a couple ways you could go about it. One way would be to recognize its numbers of hands that are full houses, so that's a discrete count, its probability, and you could think of it as a simple event if you just consider all 5 card hands as an item. So you're dealing with the 5 cards hands directly. Okay, so if we did that, we're using the equally likely counting, and we're going to jump to this counting strategy, multiplication principle with combinations. We have multiple choices, but each choice is made specifically out of a set of those things, right, and along with other choices. So what we would have here is the sample space would be the number of ways to have a 5 card hand, right? So card hand, right? And that would be, I have 52 cards, I'm choosing 5 of them, they just end up in my hand, so order doesn't matter, so that is a combination, right? I have a set of things, I'm using them up as I count them, so that would be that, okay? That turns out, I'll just leave it in that form. And then the other thing I could do, the event, is going to be the number of ways to have a full house, okay? So that's more complicated, so I'm going to use boxes to count that. Actually, there are 4 choices to make. What I have to do is I have to figure out the number of ways to pick the card to have a pair of, right? And then I have to find the number of ways to get that pair, right? And then I have to find the number of ways to pick the card to have 3 of a kind of, and then I have to count the number of ways to get the 3 of a kind. Okay, so I have to pick the pair and I have to pick the 3 of a kind. So the way you can think about this is, first of all, what kinds of cards do I have? I have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. That's a total of 13 different kinds of cards. Right, so if I have to pick a card to have a pair of, there's 13 different types of cards to pick, and I just have to pick one of those. I'll just use that combination formula. Even though it's just 13, it's really also the same as 13, choose one. All right, so let's say that I pick 6s. So that means I'm going to be saving 6s, right? Then I have to say, how many ways are there to get 2 6s? Well, there's hearts, clubs, diamonds, and spades. There's 4 suits, for there's 4 of every card. Right, so there are 4 6s in the deck, and I have to choose 2 of them, any 2 of them to be in the hand. And then, now that I've used up the 6s, I have to say, okay, what are the number of ways to pick a card to have a 3 of a kind of? So for example, maybe I pick a 9, right? Well, that means that there's only 12 cards left to choose one of to have the 3 of a kind of. And then there would be 4 of those in the deck, and I have to choose 3 of those, because I have to have a 3 of a kind. And the multiplication principle says we would multiply. So it turns out that the probability of getting a full house, just when you're dealt initially 5 cards, is out of 52 choose 5 ways, 13 choose 1 times 4 choose 2 times 12 choose 1 times 4 choose 3. There's that many hands which are full houses. When you multiply that all out, it turns out to be 3,744 full houses out of 2,598,965 card hands, and the probability is 0.00144. So very, very low probability indeed of getting a full house, which is why it's worth so much in the game of poker. Okay? All right, let's take a look at another way, though. Another way, it's actually more work, I think. This is if you did multiple events, right? The first way was if we did single events, so we considered each hand as an event, like the whole hand dealt at once. But what if I wanted to deal with each individual card? I could do that. And then I'm going to have to use my or and formulas. So I think this is a little tougher way to analyze I'm going to go ahead and say it doesn't matter which card I have a pair of and which card I have three of a kind of, if I'm talking about probabilities. Well, let's say, for example, if I analyze that I would have 2 8s and then 3 3s. So that would be an 8 and an 8 and a 3 and a 3 and a 3 in any order, right? So what would the probability of that being? Well, there's a lot of ways that could happen, right? I could have 88333, 83833. I could list them all out, and it could be all of those, each one or the next one. And then for each of those, I could figure out a probability, right? Now, the probability would have to use the and or rules. These are all distinct probabilities, so I would just add them up, right? So it would be the probability of 8 times the probability of 8, given that the first one was an 8, times the probability of 3, given that the first two were 8s, right? All those, and since it's and, we're going to multiply. And then to do these, I'll add, because each one is a fresh start with the deck, something like that. So if I were to find those probabilities, this first one, right, what's the probability that the first card would be an 8? Now I'm going to put a 1 here, because it doesn't have to be an 8. It can be any card, right? But I'm just using 8 to illustrate it. So the probability that we choose a card, well, that's going to be 1. The probability that the next card is the same as the first one, right, would be there are 3 more of those cards left in the 51 cards in the deck, right? And then the probability that the next card is not an 8 would be out of the remaining 50 cards, it's everything except the remaining 8s, which there are 48 cards left other than the 2, which are the remaining 8s. And then the probability that the next one is a 3 would be out of the 49 cards, right? There's going to be, let's see, 1, 2, 3. Yeah, that would be, there should be 4 cards, I think, right? Is that right? I have a 3 written here. Let me just check that. Oh, no, sorry. I've used up 1. I've used up this 3 here. So there are 3 3s left in the deck. And then, let's see, out of the remaining 48 cards, 2 of them would be still 3s. So if I multiplied those probabilities together, that turns out to be 864 out of 5,997,600. That's the probability of getting specifically a card, could be an 8, and then one of the same card, and then a different card, could be a 3, and then the same card and the same card, right? And then I could do a calculation for any of these other ones, and I'm going to add them up. I'm just going to go down to this one and show how this one is similar. So we would have the probability, actually, let me go down to, I'll just go down to this one right here. This one right here. So we would have a card. The probability that the next one would be different would be there are 48 cards that are not that in the deck out of 51. The probability that this one would match this one would be the remaining 3 cards of that type out of the 50 that are left. The probability that this one matches the first card would be out of the remaining 49 cards, right? There are 3 cards that are still that first card in the deck. And then the probability that this one would match the first 2 would be out of the 48, there are 2 more of those cards. And so these numbers change order, but they always involve a 48, a 3, and a 2 in the numerator, and a 51, 50, 59, 49, and so on. So these probabilities are all the same. Okay, so what I really just need to do is take that probability, 864, 5,997, 600, and add it up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So if I just multiplied it by 10, that would be the probability. And guess what? That turns out to be 0.00144, the same probability that we found when we thought of the hands all as 1. So it is possible to do this with multiple events. It's just a lot more difficult because you have to account for the different ways that they can be ordered. All right, a couple more problems here. This one says, golf balls must meet a standard for distance traveled. Balls are tested using a standard mechanical ball hitting device, which strikes all the golf balls in the same way. When hitting using a test machine, the distance to the balls traveled must not exceed 290 yards. Manufacturers want to develop balls that travel as close to the 290-yard limit as possible without going over. One manufacturer has a process that allows it to change the composition of the core of the ball to tune the distance that the balls fly on average, but there's still random variation in the distance traveled from ball to ball. The variation is normal with a standard deviation of 4 yards. If the manufacturer sets the mean distance to 284, what's the probability that we'll go too far? And then if we want to be 99% sure that we're not going to go over the limit, then what would we have to do to set the ball? Okay, so pause this and give this a try. All right, so let's give this a try here. As we look at the tree, This is our first case where we have a continuous probability, right? The variable here is the distance the ball flies. And this is not an integer. It's not counts. It could fly, say, 288.73 yards, 288.73947 yards. So this is the first case we've seen of a continuous problem. We have a probability. We don't have a PDF given, a probability density function, but we're told that the probability is normal, so that's good. So what we're talking about here is using the normal CDF function or the inverse norm function. And the first part asks us to find the probability. So that means if we need the probability or the area, we're going to end up using the normal CDF function. Okay, so let's analyze that for that. It would be this. I would start by sketching a normal distribution. And we know that this is centered at, it says, the mean distance is 284, and the standard deviation is 4. So we could set up and label a normal distribution. That means that this point out here at 1 standard deviation above would be 288, and this one would 1 standard deviation below would be 290 or 280. Sorry. And so traveling too far means we go over the limit of 290. So 290 is somewhere out here, and we're finding the probability that a ball lands in that region. So we can use the normal CDF function for that. That probability that the distance will be greater than 290 is going to be normal CDF. The lower bound of this shaded region would be 290. The upper bound would essentially be infinity. So I'm just going to put a large number in, like 999. Just has to be more than 5 or 6 standard deviations away. And then I'll use 284 for the mean, and I'll use 4 for the standard deviation. So that function is in the same places as we've been finding the binomial and those things. It's just at the top of the list, normal CDF. Okay, so the lower boundary we'll put as 290. The upper boundary is infinity. Standard deviation is 284. Or sorry, the mean is 284. The standard deviation is 4. So that would be 0.0668. So given the way the balls are set right now, there's about a 6.7% chance that if, say, an inspector came in and grabbed a ball at random to test it, that it would be over the limit and they would potentially fine the company or make them change their process or something like that. Okay, in part B, we want to be 99% sure that the ball will not exceed the maximum distance. What's the largest mean and standard deviation, right? So for this problem, we're going to have to do something a little different for part B. I'm really trying to figure out what the new mean is going to be. In other words, they're telling me, reset your mean to some other value, assuming that the standard deviation stays the same, so that if I test the ball, 290 out here will result in only, we want to be 99% sure that that the ball is in spec. So 290 out here, we want to be 99% sure. So a 99% probability, 99% of the area should be to the left of that 290 number. All right, so it seems like, you know, it's weird here. We're given a boundary and we're given a probability, right? But what we're trying to find is an unknown mean. This is what we're finding. So I can't directly use either normal CDF or inverse norm in my calculator because I have to enter a number for the mean and standard deviation. But what I can do is I can say, let's say that I were to transform everything to z-scores using the z-score formula. Z is x minus the mean, the data value minus the mean over standard deviation. Then I would get a standardized version of the normal curve. And the nice thing about that is that the mean is always 0 because the points in the middle are 0 standard deviations from the mean. And the points that are 1 standard deviation have a z-score of 1. So that would be 1, 0 and 1. And so I have a boundary here where I still have that same 99% below. And I can use an inverse norm to establish the z-score for this, right? If I use, now this time I have an area, 99%, and I'm looking for the boundary. So normal CDF isn't going to work because it turns boundaries into areas. We want to turn areas into boundaries. So we need to put inverse norm. And the way this function works is you put the left area in, which in this case is 99%, enters a decimal, along with the mean and standard deviation, and what you get out is the upper boundary of that region. So if I go to that same location and scroll 3 down to inverse norm, I need some boundary where 99% of the area is to the left if the mean is 0 and the standard deviation is 1. And that gives me 2.326, right? So this is 2.326. That's the z-score that is connected to this particular x value. An x value of 290 is connected to a z-score of 2.326. So to finish the problem, what we're going to do is we're going to say, let's look at the z-score formula. Z equals x minus mean over standard deviation, and I'll plug in what I know. I know my z-score is 2.326, and that's when the data value here is 290, right? And when the mean, that's what I'm trying to find. I don't have that, right? But I do know that the standard deviation was given as 4. So I can plug in those three values, and the only thing left to find is the mean. So you could just algebraically manipulate that. It would turn out to be 4 times 2.36. This is 9.3054 equals 290 minus the mean. And when you solve for the mean, it turns out to be 280.69 yards. Okay, so we should tune the core of the ball to not have our thing centered at 284, but to have our distribution centered at 280.7 yards. Then the probability of having a ball be too large drops to only 1%. Okay, let's see. 1, 2, 3, 4 more problems, and we'll keep going here on this video. All right, so this one says, in 2004, New York public health officials reported that 22% of adults smoked, and they increased the sales tax on cigarettes in order to reduce the rate of smoking. A year later, they checked a random sample of 1,000 New Yorkers to see if tax increase had a significant effect. What would the number of smokers need to be in this sample to convince you that the rate increase worked to significantly decrease the rate? Okay. Okay, so I was going to show a way to do this with the binomial theorem, but I think given that this is already an hour and 20-minute long video, I'm just going to jump to the correct solution here. This is really, I'll mention at least, this is really a binomial problem, right? This is really a binomial problem where you would say, I could figure out that the probability of somebody smoking is 0.22, and I could figure out the number of people out of 1,000 that smoked. And then I could try to guess different values here to see when the probability was low enough to convince me that that it's unlikely that the probability would have dropped to that number. But to use that would be a trial and error approach, which is not very efficient, right? So this is actually a situation where it's good to use the normal approximation. So we need the percentage to be lower than 22, right? But how low? We're not really sure, but it should be low enough that it wouldn't be likely to happen by chance, right? There's kind of an industry standard that says that if things they're considered significant if there's a 5% or lower probability of that thing happening randomly, just due to natural variation. So what we're really trying to do is find the percentage where that percentage or lower would occur only 5% of the time randomly, okay? Right, so like I said, we could analyze this problem using multiple trials and do a binomial, right? But I think I'm going to skip that because that's not actually the way to do the problem. Instead, what we're going to do is we're going to say, hey, if the sample size is large enough, then we can use the normal approximation to the binomial. And that's going to allow us to quickly get to the number more efficiently. So we're just going to jump to that right there. Okay, well, if we're going to do that, first of all, a binomial distribution does become a normal as long as the number of successes condition is met. So the number of successes, which is n times p, that has to be at least 10, and the number of failures also has to be at least 10. And if that's true, then we can replace the binomial distribution with a normal approximation whose mean is np and whose standard deviation is the square root of npq. Okay, and then we can use the normal CDF and the inverse norm ideas, right? So let's check this problem. Let me actually get rid of this. Actually, let me just go back to the problem statement. We'll do it here. Okay. So first of all, can we use a normal approximation? Okay, so we have to check the number of successes. So that would be N times P. We have 1,000 smokers, right? If 22% of them smoke, we would expect there to be 220 smokers. That just has to be at least 10, and so that's definitely true. We also should check the number of failures. That would be N times Q, so that would be 1,000 times the remaining, let's see, remaining, what is that? 78%, right? Which would be 780. It is 78, right? Okay. Yes, okay, 780, and that's also 10, so definitely that qualifies. We have definitely a large enough sample here where no matter what the p-value is, even if it's far away from 0.5, the shape is going to be normal. Okay, so if that's true, then I can just say, I can model this with a given mean and standard deviation. The mean is going to be NP, the number of successes, which is 220. So we would expect 220 people out of this 1,000 to smoke, right? The standard deviation we'll have to calculate. It's the square root of N times P times Q, which would be the square root of 1,000 times the probability of somebody smoking, 0.2, times the probability they don't smoke, which is 0.78. And that turns out to be 13.0996. I'll just abbreviate that, 13.1. 13.1, 13.1. All right. So what we're saying is, you know, the one standard deviation above the mean would be if 233 people smoked, and one standard deviation below the mean would be if 207 smoked. So the question is, if this taxation worked to decrease smoking, then this number should be going down, and it should go down to the point where it's unlikely that we'll have that just randomly, right? So I mean, we would expect that if you sample 1,000 New Yorkers, we're going to have a different amount of people who smoke, right? But if I can get this boundary value here where there's only a 5% chance that it happened randomly and maybe therefore not due to the tax increase, then I'm pretty sure that that is due to the tax increase. Okay, so if I'm trying to go from an area to a boundary, that's where I need my inverse norm function. So inverse norm, right? 5% of the people would be low anyway, just due to randomness, if the mean was 220 and the standard deviation was 13.0996. And if you plug that in a calculator, that turns out to be 198.45. Since I want to go to the left here, I'm going to round that down. So basically, if we took a sample of 1,000 smokers and only 198 of them smoked, when we expected 220 to smoke, that would be enough to convince me that the tax increase did have its desired effect. Okay, a few more problems here. For this one, it says, in the old days, before digital video recorders with time-shifting capabilities, if you wanted to record a show to watch later using a VCR, a video cassette recorder, you had to wait until the show finished recording to the end before you could watch it from the beginning. So suppose you set your VCR to record your favorite show because you knew you had an appointment and you wouldn't be home before your show started at 7 p.m. So you set the recorder to start at 7. The earliest you could be home would be, say, 7:15, and it's likely that you would be equally likely to get home anytime between 7:15 and 9 p.m. when your show ends. So we're going to add that this is the end time for the show, when the show ends. Okay? Okay, what's the probability that you would have to wait more than 30 minutes to record before you can watch your show? And what's the typical amount of time you should expect to wait to watch your show once you arrive at home? So pause this and then give it a try. Okay, so when I look at this, I'm thinking strategy-wise, definitely this is a continuous probability problem because you could wait any number of minutes, including decimal minutes. It's a probability problem. We don't have a PDF given, but in this case, the wording that says we're equally likely to arrive home in any time means we have a uniform chance. We have an equal chance of probability of any of the times between some boundaries. So we're going to try to come up with a uniform probability model, right? And it's this right here. For a uniform model, the probability density function is just going to be f of x equals some constant, right? We just have to make sure that the area under the curve equals 1. And then we'll use an integral to find the area under the curve between any boundary, which is a sub-area there. Okay, so let's say that I've got this, right? Here's the time, okay? And actually, let's plot this as this is probability versus wait time, right? So what's the smallest amount of time we could wait? Well, it said we could arrive home right at 9, right when the show ends. So we could wait 0 minutes, right? Or we could arrive at home at 7:15, which would be, let's see, that's an hour and 15 minutes. So 60 plus 15 would be, is that right? No, wait, that's 2 hours, right? 2 hours. Well, wait a second. 7:15 to 9 p.m., right? So if we go back to 8, that's 1 hour. And then 7:15 to 8 is another 45 minutes. So it's going to be 60 minutes plus 45 minutes, 105 minutes. So it looks like from a quick calculation, we can determine that the maximum amount of time that we can wait is 105 minutes. Okay. And we're equally likely to wait any of those amounts of time. So the probability density function here would be uniform. What I do know is that the area in this has to be 1. So if this width here is 105, then hopefully you'll agree that this height would have to be 1 divided by 105, so that the area, the width times the height, 1 over 105 times 105 would end up being 1. So that's how I'm going to determine that the probability density function, f of x here, is just the constant 1 over 105. That's the first thing, is we need to know what the probability density function would be, and we'll have to build it from the words. So then we're wanting to find the probability that we have to wait more than 30 minutes. So that would be, maybe 30 minutes is here, and we want the probability that we wait more than 30 minutes. So that would be that area. So since this is not a standard curve where we already have a PDF or a CDF function in there, we're going to have to use calculus for that. The probability that the wait time is greater than 30 minutes, that's going to be equal to the integral from 30 up to the maximum value of 105 of the PDF, and the PDF is 105, 1 over 105 dx. Okay, then I could use calculator features like the if you have a calculator that does the integral directly. I'm just going to do it that way since this isn't really a calculus video. 105, and I'll enter 1 divided by 105 here for the PDF and then the variable key. And so that turns out to be 0.7142. So 0.7142 is the probability. In other words, 71% of the area is between 30 minutes and 105. Okay? Okay, for the second part, it says what is the typical amount of time that we should expect to wait. So for continuous problems, we have two definitions of typical value. We have expected value and we have average value. And the difference is what is the f of x. If the f of x represents the values, then we're having to take the average of the values. And so we use the integral to add up the values, and we use the interval size to divide. It's like adding up the total and dividing by the number of elements. Right? But if the f of x is a probability density function, then it's not the values. We have to multiply that by the values and then integrate over the entire region. This is like the continuous version of x times probability. Right? It's a sum of data values, x, times their probabilities. So we're going to use the expected value formula here. Right? The expected value formula, right, would be an integral over all possible wait times, 0 to 105. Of an x times the probability density function, which is 1 over 105 dx. And we can plug that in a calculator, math 9. So it's going to be from 0 to 108, or sorry, 105, with an extra x in there times the probability density function 1 over 105, and then dx. So that turns out to be 52.5. So on average, we should expect to wait 52.5 minutes when we get home before the end of the program, so that then we can start watching. All right, just a couple more to go here. Let's take a look at this one. This one says, for graphic design work, a particular graphic designer charges $50 per hour plus a fixed setup charge of $200. If the time required for graphic design jobs varies normally with a mean of 30 hours and standard deviation of 14, how does the distribution of charges per graphic design job vary? So pause this and give it a try. Okay, in this problem, essentially we're trying to transform, what are we given? We're given that something varies normally. So actually, let me look at the chart again. This is a continuous problem. Both fees and hours are continuous variables, any possible number. It's a probability problem or not. I think, yeah, this we're actually trying to figure out the mean and standard deviation. But we're told that this is a normal distribution, and we have changing units and quantities, right? We're changing from hours of time into the units of dollars for the job, right? So we're basically transforming that. So What we can remember is this. When we transform a distribution, multiplying or dividing affects both center and spread, but adding and subtracting affects only measures of center, because if you shift things around, it doesn't change things like standard deviations or IQRs. All right, so maybe what I would do is say, let's do a distribution for the hours, because they told me it was normally distributed, right, with a mean of 30 hours and a standard deviation of 14 hours, okay? So this is my mean of hours, my standard deviation of hours, right? And what I'm really trying to do is transform this into a new distribution for the fees, right? It will also be normally distributed with some mean for the fees and some standard deviation for the fees, and that's what we're trying to compute, that mean and that standard deviation. So the transformation is done this way, right? It says that if you think about transforming it, it's $50 an hour. So if I were to kind of say this, I could maybe make an algebra equation that says the fees is equal to the number of hours, and we're going to multiply by $50 an hour, plus we're going to add a fixed setup charge of 200. So we're multiplying by 50, and we're adding 200. That's what's happening to transform the hours into the fees. All right. So the mean of this distribution, so the mean of the new distribution, right, fees, well, the mean is a measure of center, right? And we know that individual measurements, including center, they're affected by both the multiplication part and the adding and subtracting. So that means that the new mean will be the old mean, which is a mean of hours, times the multiplier of $50 an hour, times 50, and we're also going to add the $200 fixed fee. So the new mean would be the old mean, which is 30, times 50 plus 200, and that turns out to be equal to $1,700. So this would be $1,700 here, is the mean. So the average that this graphic designer will make on a job is $1,700. Okay, for the standard deviation, for the fees is going to be the standard deviation for the hours, but multiplied by the 50, because multiplication affects both things, right? Multiplying affects both center and spread, right? But the adding affects only center, and that means since this is not a measure of center, the adding part, the plus 200, that will not affect this number. So we're only going to do the multiplying part. So this would be that the old standard deviation was 14, so the new standard deviation will be $700. Right, so the standard deviation of jobs in terms of money will be 700. You might write it this way, that the fees are normally distributed with a mean of 1,700 and a standard deviation of 700. Okay, so this is an example of transforming. And then once we have that, we could use that to do probability, like what's the probability that we'll make more than $3,000 on a job, or what's the probability we make less than $1,000 on a job, or something like that. Okay, last question. Suppose that a particular nightclub, the heights of men and women were each normally distributed, with the men's height having a mean of 69 inches, standard deviation 5, and the women's height mean of 64 inches, standard deviation 4. If one female and one male were randomly chosen and paired to dance, what would the probability be that the woman would be taller than the man in that couple? So pause this and give it a try. Okay. So if we look at this, this is, again, a continuous variable, inches. It could be at decimal inches, any number of inches. It's a probability problem. We don't have a given PDF, but we're told that it's normal, and we're dealing with multiple distributions of men and women that are different. So we're going to use the distribution combining rules. And they're basically this. If you can write out an algebraic expression for how the variables are being combined, the mean will exactly follow that algebraic expression. But the way the variance works is we apply something called the Pythagorean theorem of statistics. So it's not that the standard deviations combine linearly, it's that the variances combine. And the way I think of it is every time I add another distribution that varies, we have to add another variance for that. And it doesn't matter whether we have adding or subtracting, every time I add a new source of variance, the variability increases. Right? So the way you can think of this problem is we have a distribution for men, right, for their heights, centered at 69 inches and standard deviation of 5 inches. And we have a distribution for women, right? Their heights are centered at 64 inches with a standard deviation of 4 inches. Right, so what I could do is define, say, a new variable. Let me define a new variable. I'm going to call it the difference, and it's going to be the man's height minus the woman's height. Well, if that's true, then that will also have a distribution. It's going to have some mean of the difference and standard deviation of the difference. Okay? So if I algebraically wrote it, I could say the difference is the man's height minus the woman's height. Right? The reason I'm doing it this way is I'm really trying to investigate the probability that the woman is taller. So if the woman were taller, then that means if the woman is taller, then that means that D will be negative, right? If D is negative, then that means that the man's height was smaller than the woman was taller. Okay, so first I need to investigate the distribution here, this mean. So for the mean of the difference, that's going to follow this algebra equation. It's the mean of the men minus the mean of the women, right? So that would end up being, the mean of the difference would be, the man is average height is 69 and the woman is 64, so the mean of this difference would be 5. Nope, I'm going to replace this here. This right here is 5. The average difference is 5, where the man is 5 inches taller. For the standard deviation, we're going to use the idea that variances add. The variance of the distance is equal to the variance of the men plus the variance of the women. The reason this is plus, even though this is algebraically negative, is that when I add variation from women, it always increases the amount of variation. Right? So the variance for the difference would be the standard deviation of the men, 5 squared, plus the standard deviation of the women, 4 squared. And so this would be the square root of 5 squared plus 4 squared, which is the square root of 41, which is 6.4031. So these standard deviation numbers here, 6.4031. Okay? Okay, now I'm going to switch to the probability problem. Now I know that for the difference, we have something which is centered at a difference of 5 inches with a standard deviation of approximately 6.4 inches. Right? So what that means is plus 1 standard deviations would be around 11, and minus 1 would be at around -1, right? Actually negative 1.4 and 11.4. Right? So what I'm saying is that we're trying to find the probability, find the probability that a woman is taller. So that's the probability that D is less than 0, that it's negative. So somewhere here is where 0 happens, and I'm trying to find the probability that that's true, that we would have a negative value. So since that's an area with a given boundary, I can do that with a normal CDF function. Normal CDF, right? The lower boundary would be something representing negative infinity, like -999, and then up to 0. If the mean of the differences is 5 and the standard deviation is 6.4031. 4031, right? So then you would go to the calculator to plug that in. Let's see, we've got normal CDF from negative infinity to 0 as the upper boundary if the mean of the differences is 5 and 6.4031 is the standard deviation. That turns out to be 0.2174. Okay, so in this particular nightclub with this distribution of men and women, there's about a 22% chance that if you randomly pair a man and a woman, that the woman would be taller. All right, so lots and lots of problems worked out there. I hope you found these videos to be useful. Remember, you can go back and look on the strategy sheet at the numbers. That tells what previous video lessons cover each of the topics if any of these ideas weren't clear. Thank you for watching.